Big fan of scanf, the function commonly used to read input from the console. It's problematic in so many ways. It's simpler just to write discrete console apps that read instructions from the command line arguments. Still, if you need to read individual values from the console, there's a way to do it. Scanf is not the only way, but it's a common and portable way, so let's take a look. Let's say we need to get 3 numbers from the user. We can use scanf with a format string specifying how to interpret the input and where to place the resulting values. Notice each of the scanf arguments are pointers. We want scanf to write values to the locations indicated by these pointers. And then let's print them out just to make sure we read everything correctly. First, let's try GCC. And again, GCC has no problem with scanf. Let's enter some values. Great. It was able to scan the input and find 3 numbers. What about something a little different? Even though I hit the Enter key, scanf is not satisfied and will simply wait until more numbers are provided. Oops, that was 1 too many numbers. Oh well, scanf is finally satisfied and prints out the first 3. So scanf is messy, but it appears to work. What about Visual C++? The compiler is once again unhappy with the very use of this function and suggests we adopt the secure alternative. Why? What could possibly go wrong? Well, what if we wanted to read a string? There's a buffer that will receive the string to be read. And then scanf with a character string format specifier and matching pointer. And then let's print out the captured message. Looks wonderful. We'll just ignore the warning for a moment. And it captured the word hello. Great. Now, what about a slightly longer word? And we have a problem. Again, scanf captures the word, wrote it to the array, but it overflowed and corrupted the stack. And again, this is only discovered after the buffer overflow, the printf call, and the main function returns. A disaster waiting to happen. This is where the secure scanf function comes in. The secure version of this function expects the buffer size to be specified at runtime. Now, scanf_s knows how many characters are available to write to and will not go any further. Let's try. Thankfully, the warnings are gone. A short word works fine. How about a long one? Nothing. Scanf_s realizes that the buffer is not large enough and doesn't attempt to write the input. Now, we can still opt to have the input truncated, but at least now it's safe. This time, the first 9 characters are safely copied to the buffer as requested. The printf and scanf functions that we've used thus far are just an abstraction over the larger I/O stream facilities that cover not only console input and output, but input and output from files. They share a common interface, so to speak, such that you can direct input and output requests to either with the same set of function calls. You might want to write an application that either prints its results to the console or to a file based on some command line input. No problem. Along with printf and sprintf is fprintf. That's right, file printf. And while we're at it, I'll just skip straight to the secure version provided by Visual C++. The first argument is a file handle, then the usual format string and any values. Now we can use one of the standard I/O streams. They have macros defined for them. An embarrassing lowercase macro, but a macro nonetheless. But this is no different to calling the vanilla printf function to print to the console. Great. Still, it's useful as an abstraction since you can write a program that will write to different targets without having to duplicate the code, without having to know exactly where they're writing to. I might instead want to write to a certain file. For that, I can use the fopen function, or its secure replacement. So firstly, it's possible this function might fail for a variety of reasons. This temp folder, for example, is assumed to exist. If it doesn't, fopen will fail. So that's why it's important to check the result, the return value. The final parameter is also notable. Here, W means write. We want write access to the newly opened or created file. Now if it fails, if it's something other than 0, it represents an error code, telling you what went wrong. We could return this value or print it out, but that wouldn't be very helpful to the user. Instead, let's look up the description. First, we'll need a buffer to hold the description of the error message. Then we can call another function to look up the error code. This is another secure alternative to an older standard library function, which checks the buffer for sufficient space. It's declared for us in the string header. Then we can print it out and end the program. Otherwise, we can assume the file was opened successfully and we can print out a message. But let's not forget to close the file handle, a resource we're responsible for. Okay, let's give it a try. No crashing, that's a good sign. What about our message? Did it get saved to the file? Sure enough, there it is. We successfully used printf to write to a file. It's tempting to leave it there, but let's just check that our error handling works. Let's use a bogus path. We'll recompile, run, and no such file or directory. Excellent. We can now use everything we've learned about printf and apply it to file output. In this module, we've explored the standard input and output facilities provided by the C standard library. Printf remains the most efficient general-purpose output formatting engine to both C and C++ programmers. I do encourage you to use the secure alternatives for string and file output, if at all possible. Scanning for input is problematic at so many levels, but if you need to do as much, be sure to use the secure version of scanf. Finally, we covered file output and the abstractions for supporting console and file output seamlessly. This is great for reporting and just general text output.